All right, thank you everyone for coming to GOCC this week. This week we have lovely Gabe from Cornell to talk to us about the expected value in enumerative combinatorics, permutations, puzzles, and parking. Before we begin, we can go over a community statement. So we are all learning, everyone has something to contribute, and no one has all the answers. So with that, take it away, Gabe.
Hello. Thanks for the introduction. So I'm going to have two parts of this talk. The first part is going to be about knights and knaves puzzles, and the second part is going to be about parking functions and things relating to parking functions. And I wanted to present these two materials together because in both projects, there were these expected value proofs, which were very simple and easy and kind of the same as each other or very close to each other. And one project, like the proof in one project kind of inspired the proof in the other project. So some sort of big ideas are if you're trying to compute the sum of something over a set, you might reframe it in terms of expected value to go from computing like the sum of some function f of x over little x's in a set big X to expected value. You just divide by the size of your set x. Also, sometimes when there's symmetries, things are extra, extra nice. And that's the case in the examples that I'll talk about. And in my opinion, sometimes expected value arguments can feel more explanatory than bijective arguments. So I am like all about the bijective arguments everywhere. I want bijections for everything. Um, but sometimes the bijection isn't the right way to go. So like a classic example of that is if you have unimodular tilings, wait, is that the right word? Well, it's okay. Unimodular tilings of a polytope, then any two tilings are going to, triangulations. Unimodular triangulations of polytope, any two triangulations have the same number of simplices, but there's not always going to be a nice bijection between them. And I think sometimes when there's symmetries, there might be bijections, but the expected value arguments can be sleeker. And the other thing I'm going to talk about is this tool of asymptotic independence. Okay. So in the second part, I'm going to talk about some of these results, and we're not going to talk about this until then, but I wanted to give a preview. That basically we do a thing which gives these easy arguments that help us compute totals of a bunch of statistics. So these are the second column is permutations and the third column is parking functions. And these formulas are for totals of statistics over the entire set of permutations. So you look at every permutation and you add up the number of inversions, or you look at every parking function, you add up the number of inversions. And we get all these formulas, and the OAIS sequences with like the daggers on them are like new OAIS sequences that came from they're for the formulas directly to the left of them. They weren't in the OAIS before. Okay, so now we'll get into parking function, sorry, knights and knaves puzzles, and we'll come back to parking functions later, and I'll tell you what they are. Okay, so all trolls are either knights or knaves. Knights only tell the truth, and knaves only tell lies. So here's, oh shoot. I'm realizing I forgot to put some pauses in here. Um, that's okay. Okay, so here's two example puzzles. You go to a group of five trolls and you ask each one how many knights are in this group, and everyone tells you a number. Um, so the question is, how many knights are there really? So look at these problems. If your birthday is an odd number, look at the first one. If your birthday is an even number, start with the second one. And then I want someone to tell me the answers to these puzzles, and I will wait. Oh, but you probably have to speak up because I can't see everyone. So if you're like raising your hand, I'm not going to notice. I'm going to just wait for someone to speak up.
the first one, there should be none, probably,
There should be none. So why should there be none?
because if there is a if there are, if there is someone, then either the correct answer is one or three, and there cannot
Okay.
be one because three of them would be telling the truth, and there cannot be three because only two of them tell the truth.
Yeah. How about puzzle number two? Anyone have a thought there?
I think it's one.
Yeah. So in puzzle number two, there's one troll that says one. So that one troll could be the truth teller or the knight. Um, you can't have any of the other things, and also you can't have zero because someone says zero. So if the answer was zero, they themselves would be telling the truth, which would make them not telling the truth, and there's sort of a liar's paradox there. So what's going on here is an n-troll puzzle is an ordered partition of n into n plus 1 non-negative integer parts. So we have parts a0 through an, where a0 is the number of trolls who say that there's 0 knights, and a3 is the number who say there's 3 knights. And these numbers have to sum up to n because there's n trolls. And a solution is some as, which is equal to s. So if 0 people say 0, then maybe everyone's lying. If one person says 1, then maybe they're the person who's telling the truth. If 2 people say 2, then 2 is a viable solution. Okay, so we want to count solutions in puzzles and think about how many solutions each puzzle has. So some puzzles have no solutions. This is an example of that, where there's no sort of fixed point to this ordered partition. There's no a sub I equal to I. And some have multiple solutions. In this puzzle, 0 is a possible solution, 1 is a possible solution, 2 is a possible solution, and 3 is a possible solution. The number of distinct puzzles is n plus 1 multi-choose n, or like you have n plus 1 different possibilities. People can say between 0 and n, and then each of the n people kind of get to choose one of those things. And by like a balls and walls argument, this is 2n choose n. So our main questions are how many n-troll puzzles have a unique solution, how many have no solution, and how do these quantities compare with 2n choose n? So here's some plots. This is what happens when you plot. So in blue, we're seeing the proportion of puzzles which have 0 solutions. Red is the proportion with 1 solutions, and so on. And you can see this is only going up to n equals 10, and it's flattening out extremely fast. If you go up to n equals 1,000, the plots just look flat. I have almost in no other context seen plots which seem to converge to something like this extremely. So what are they converging to? Why do they converge to anything at all? What's going on? This project I worked on with mostly with Eob Tsagaye, and it was given to us by William Gasarch when we were at the end of high school. So we started thinking about this in like the end of senior year of high school, and we, kept thinking about it during college and tried all sorts of things and kind of didn't get anywhere. And then at the end of college, we'd like done a math major, each of us, um, and had enough tools to kind of answer these questions. And now we're both applying to postdocs, and I have new research to talk about since then that's kind of similar. Okay, so what are some of the things we tried? We tried inclusion, exclusion. This provides no insight. We kind of generalized to also have this extra parameter p saying the number of people there are. And n here is like, you can say the numbers you're allowed to say are between 0 and n. That didn't really help that much. We had a recursion relation, not that good. I liked this generating function, kind of, but we didn't really make anything of it. I sort of tried to use the circle method on it. I didn't get anywhere. None of this really worked. Um, so I'm going to take a step back and say, um, and talk about this other piece of this, and then we'll come back to the problem of understanding those graphs. So there's this paper that looked at counting knights and knaves puzzles by Levin and Roberts in the Journal of College Mathematics. And they showed that this sum over all S of S times the number of puzzles with S as a solution, or sorry, with S solutions is 2n choose n. So the left-hand side of this equation is the number of puzzle solution pairs. So you have a puzzle and you have the true answer behind it of this is how many knights there are. And the right-hand side is the total number of puzzles. So why is the total number of solutions across all puzzles equal to the total number of puzzles? They had a direct proof of this equality, and then they did a bijective proof. And here is their bijective proof. So if you start with a puzzle, which is this list A0 to AK, you'll send it to a puzzle solution pair where you look at A0, and if A0 is 5, you switch the number of people saying 0 and the number of people saying 5. So you're doing this switch. So now A0 was 5, now A5 will be 5. And since A5 is 5, that's a viable solution, and that's the solution you map it to. If you didn't get the details of that, it's okay. This is a bijection. This does the proof. And I think there's insight in here, but they kind of concluded their paper with, this doesn't feel that insightful. Is it actually insightful and we don't see why? Or is there a better bijection? And like what's going on with this where the bijection doesn't really seem to be answering the why question as satisfactorily as we want. Okay, so let me just peek at the next slide because I'm gonna okay. So my sort of response to this is expected value gives you more intuition. So if you have a random variable x that can take on values x1 through xn, then the expected value of x is this sum over all these possible values of xi times the probability that x is equal to xi. Expected value has this lovely property that it's linear. So if you can write your random variable as a sum of other random variables, then you can break up expected value across those pieces. And another piece here is that the indicator variable 1a, we're defining to be this variable which is 1 if the event A happens and 0 otherwise. And the expected value of an indicator variable is the probability that the event happens. Okay, so based on these ideas, does anyone have any guesses for... Ooh, I don't... Somehow my keys don't work for moving slides. Anyway, does anyone have any guesses for a different proof that the number of solutions is equal to the number of puzzles or thoughts?
Show that the expected number of solutions is 1.
Yeah, if we show the expected number of solutions is 1, then we'll be proving the same thing. So now any guesses for how we might go about showing the expected number is 1? Steps we might take that maybe will work or not.
Sum over the probability of each number being a solution.
Yeah. So we'll sum over the probability of each number being a solution. Expected value is going to break up over each of those possibilities. And I wish I had pauses, but I don't think I do. So here's the rest of it. Here we're letting S of A be the set of solutions. So our expected value of the number of solutions is the expected value of this sum, where we have these indicator variables for whether each I is a solution. Those are just the probabilities that AI equals I for each I. And then the thing that makes this proof go through is that the probability of AI being I is the same as the probability of A0 being I. Because if you take a puzzle and you mix up the numbers, it's still a knights and knaves puzzle. So these AIs are all identically distributed, and when we sum up this, now we have this sum of the probabilities of A0 being I for all I. Well, A0 is something, so these probabilities sum to 1, and then we're done. So to me, the right proof of this identity comes from two things. One, this linearity of expectation, and two, this symmetry property or equidistribution of these AIs. Yeah, so that's this proof. In this second part of this talk, we'll come to look at a very similar proof that sort of uses the same feeling. But for now, we'll talk about the resolution to oh, is there a question? No. Anyone can stop me with questions anytime. But anyways, we'll move on to the resolution of this problem of like these graphs converging really fast and there being a fixed proportion of puzzles with any number of solutions. Okay, so we're gonna have this AN be a random puzzle and we're gonna index its pieces by n and then I, just so we know how many, just so we know what n is. And then we'll say ANM is 0 if m is bigger than n. So it's like no one is saying 100 if there's only 10 people. And we're putting that in the data so we can kind of be consistent. Then we say this S of AN is the set of solutions to this puzzle, this random puzzle. And we can compute the probability that I is a solution, which will be 2n minus I minus 1, choose n minus 1 over 2n choose n. This is because we need to, if I is a solution, then there's I people saying I, and the remaining n minus I people have only n minus 1 options. And when you do the balls and walls calculation, you get 2n minus I minus 1, choose n minus 1 for the number of ways that can happen. If we expand this, we get this thing that if you stare at this fraction, you can be like, oh, that's really, really, really close to 1 over 2 to the I plus 1. So when you take the limit of this probability, oh no, this yi is not defined. I'm so sorry. This yi should be the probability that I is a solution to the puzzle AN. But the probability that I is a solution to the puzzle AN is 1 over 2 to the I plus 1. Then we can start looking at multiple of these at a time and say, what's the probability that the set of viable solutions to a puzzle contains some list I1 through IN of distinct possible solutions. And when you do a similar calculation and you take the limit, it's 1 over 2 to the m plus the sum of those ij's. So a thing is happening here that's very spooky. Oh, so sorry, m was the number of these pieces. This probability is what you would expect the probability to be if all of these were independent variables, but they're not independent variables. So, and it's like if you took their limiting probabilities to be their probabilities. So we can kind of model the situation in the limit with independent variables. So we take zi to be an the set zi to be independent Bernoulli variables with the probability. So a Bernoulli variable is something that's either 1 or 0. And these are going to be 1 with probability 1 over 2 to the I plus 1. And then we can show this stronger result that the limit as n goes to infinity of all of these y and ij's being 1 and everything else is 0 is the same as the thing that you'd expect if you do something similar with these Bernoulli variables. So what this is saying is that in the limit, the probability that your solution set is exactly I1 through IM is the same as if you took these limiting probabilities and just multiplied them together as if everything was a random variable. So the way that we get to the end here is we have our same setup with these y and i's being these indicator variables, and the zi's being these Bernoulli variables, and we'll define this sequence of things kind of approximating the answer. So we'll let HNKS be the probability that Um, the number of solutions less than k is s. Oh, sorry. So this is the probability that there's s solutions and they're all less than or equal to k. So you have this many solutions and all of them are small. And we'll let pks be sort of this more easy to deal with thing modeling this situation where we say we're going to determine if I is a solution by flipping a weighted coin. And we don't care that these things are actually dependent. We're going to pretend they're independent Bernoulli variables. Then we can compute this limit by doing the first line is like what just by definition. And the second line is saying, actually, these HNKSs are really close to the thing we want. And the reason they're really close is that the probability that you even have a single solution bigger than k is like 1 over 2 to the k. So most puzzles don't have a solution bigger than 7, but most puzzles don't have a solution bigger than 3. And as you push that number bigger, the proportion that you're talking about gets smaller and smaller and smaller. So this HNKS is actually a very good approximation of the probability that you have S solutions. And then from this HNKS, as you take this limit as n goes to infinity, it turns into the situation with these Bernoulli variables. And then as we take k to infinity, we just have this infinite sequence of Bernoulli variables. So you flip one coin that's like 50-50, and then you flip another coin where there's like a 1/4 chance of getting another solution, and then the next coin gives you a 1/8 chance, and so on. And then you get this distribution coming from that, and that's the limiting distribution. So the key tool here was this asymptotic independence where you didn't have independent variables, but it was almost as if you did. So what are these numbers? Well, p infinity 0, this is the limiting probability that you have no solutions, turns out to be this infinite product that you can write with this Q Pockhammer symbol, and it's about 0.288788. A fun fact is that this is also the limiting probability that a binary matrix is non-singular. I think it's a complete coincidence that these two limiting probabilities are the same, but I really like the fact that they are. You can write the limiting probability that you have exactly one solution as this product where this E is this spooky Erdős-Berwain constant, and you can write down formulas for P infinity S. So that's kind of the end of that story. But it was, I don't know, it was very satisfying to kind of start a project at the beginning of undergrad and then complete it at the end, having learned more things. Any questions right now? Okay. We can come back later if we want to. So, oh wait, there's another fun thing here. So we could modify our puzzles to have these clever trolls who are trying to trick you. So if you ever have 5 trolls say 5, then the next troll isn't going to say 5 also, because then they would make the puzzle easier for you by reducing the number of possible solutions. So we're thinking about puzzles where you never have more than I people say I. When you do this, you can use a bijection, like a Lemma code bijection, to biject the puzzles with these new puzzles with k solutions with permutations in Sn+1 that have n inversions and k left to right minimums. So when you have k equals 1, this is just a bijection with permutations in Sn that have n inversions. And using some asymptotic formulas on the OEIS, it seems like this means that the limiting proportion of puzzles with a unique solution is 1/2, which is kind of fun that when you change the problem a little bit, it becomes about permutation statistics, and there's a much easier answer. Okay, So now we're actually going to talk about permutation statistics and that sort of field of things. So this is joint work with Kyle Solano, Jennifer Elder, Kimberly Hadaway, Pamela Harris, and Amanda Priestley. This was started at the graduate research workshop in combinatorics, and the problem was proposed by Kimberly. And it's largely about parking functions. So what's a parking function? These were introduced by Conham and Weiss, and the idea is that you have n cars parking in n spots on a one-way street. So once you pass a spot, you can't go back to it. And each car has a preference for where they want to park. And these preferences will be that the ith car wants to park in spot alpha I. So what happens? The car drives to its preferred spot, and if its preferred spot is empty, then it parks there. And if it's not empty, then it keeps driving and it parks in the next available spot. The place where I currently live is full of one-way streets, and this is very much like my reality sometimes. So a parking function is a sequence of preferences where all of the cars get to park on the street. None of them have to drive around the block. And here's this illustration of the parking process where this first car prefers the second spot, so it parks there. The next car prefers the fourth spot, it parks there. The next car prefers the second spot again, so it can't park there, parks in the next spot, the third spot. And then the next car prefers spot 3, can't park there, try spot 4, can't park there, try spot 5, parks there. So these are what parking functions are. Any questions on parking functions for this moment? Feel free to ask them later too.
So car 1 always parks in spot 1. That's not a coincidence here.
Here car 1 is, so the numbers written on the cars in the picture are the preferences of the cars. And car 1 is the first car to park. So car 1 is this car labeled 2 on the very end, the light blue one.
Sorry, I mean car with preference 1 always parks in its spot. There's no way to be
Not
taken.
necessarily. So one example of a parking function is this is just n ones. So if you have n ones, every car wants to park in the first position. The first car to park gets to park there, but the next car can't park there and goes to the spot after.
Oh, they don't need to be different. I thought everyone.
Yeah, they don't need to be different. So
Okay.
they aren't necessarily permutations. So, and here in this example, we have two twos. Other questions on
All right.
parking functions?
Okay, thank you very much.
Yeah. Okay. So here's some facts about parking functions. Every permutation is a parking function because in a permutation, that's every car having a different preference, and then they'll just all park where they want. There's no conflicts. If you take a parking function and then you mix up the numbers, you will still get a parking function. So any permutation of a parking function, as in like taking the same numbers in a different order, is still a parking function. And a stronger fact is that alpha 1 through alpha n is a parking function if and only if for every I less than or equal to n, at least I cars want to park before I plus 1. So if you sort the list and now it's in increasing order, then oh gosh, what's the statement there? The first, actually, I'm not going to try to translate it. Sorry. It's a very simple translation, but one should not do math live, even if very simple. So, but yeah, you can just look at the rearrangement to an increasing thing and check that way if it's a parking function. And when you do that and you look at what are these weakly increasing parking functions, there's 1 over n plus 1 times 2n choose n many of them. So Catalan many, and that's very lovely. So parking functions include permutations, so in that way they're generalizing permutations, and they have this connection to Catalan numbers, and they also have this connection to the shuffle conjecture and other mathematics. Oh no, so a formatting thing happened here, but this should be there's n plus 1 raised to the n minus 1 power many parking functions. There's also a bijection between parking function, well, many bijections between parking functions and rooted labeled forests. And we'll denote the parking functions of length n by PFN. So an L interval parking function is one where, first we have to define the displacement. So the displacement of a car is the distance between where it wants to park and where it actually parked. And an L interval parking function is one where every car has displacement less than or equal to L. A unit interval parking function is an L interval parking function where L is 1. So every car either parks in the spot it wants or in the spot right after. So the project started by being about computing statistics on L interval parking functions, and specifically these unit interval parking functions where L is 1. So here's 2 examples. This first thing is a unit interval parking function. The first car parks in the 9th spot, next car in the 4th spot, next car in the 6th spot, next car in the 1 spot, and the car after that parks in the 2 spots. So that one has a displacement 1, but it's okay, it parks in the 2 spot. Next car parks in the 5 spot. Now this 2 can't park in the 2 spot, that's filled, so it parks in the 3 spot, and so on. The one below it though, if you change that 2 to a 1, that car that wants to park in the 1 spot can't park in the 1 spot, also can't park in the 2 spot, has to park in the 3 spot, and that's a displacement of 2, so it's a 2 interval parking function, not a unit interval parking function. So I'm not going to prove this theorem, but it turns out that these unit interval parking functions have a very, very nice structure. If you rearrange your unit interval parking function to be strictly increasing, then you get something that has very, very nice structure. These A1 primes through AN prime will have the property that AI prime is either I or I plus 1. And we can put these separators between spots before each element AI prime where AI prime is 1. And then we'll get these blocks that we've separated out. And each block is going to be of the form I plus 1, I plus 2 through I plus j. What's happening here is when you sort of think about your unit interval parking function, there's going to be like a car that parks where it wants, and then there might be a car that wanted to park there and parks in the next spot. And you might have a car that wanted to park there and parks in the next spot. And you have this chain of slightly dissatisfied cars, but you can't have sort of long range effects beyond that happening. You can just have these chains of cars and then some cars that get to park where they want. And yeah, and the sizes of these blocks determines exactly what's going on here. Okay. So this, oh yeah. Stefan?
Just a question. Like,
Yeah.
can't you have that scenario where, for example, say you have 2, 2, 3, 4, 5, and if that sequence keeps going up, then you get a really, really long chain that's
Yeah.
essentially the whole sequence.
So you'd need to have something park in the 1 spot, but you could have 1, 1, 2, 3, 4, 5, 6, 7, etc. And that's the whole thing, and there's just 1 block.
Yeah. Okay.
Did
But
that
even
answer the
with 2,
question?
right? Kind of, because even with 2, you could essentially have the first slot be open forever if the first 2 numbers are 2, right? Because everything goes to 2 first, and then it can't go back. So slot 1 would be perpetually empty.
So to be a parking function, because you have n cars and n spots, every spot
Okay.
has to be filled. So some car has to want to park in the first spot.
Got it.
That's so, sorry, I kind of glossed over this because I had a moment of confusion. But this thing about for every I less than or equal to n, at least I cars want to park before I plus 1. So this is just for parking functions in general. Sort of thinking through, why is this true? Well, some car needs to want to park in the first spot. Otherwise, the first spot will be empty. So that's what this is saying for I is 1. And then some other car has to want to either park in the first or second spot. If they want to park in the first spot, they'll park in the second spot so that those two spots are filled. And it sort of continues where you need at least 3 cars that want to park in the first 3 spots. Otherwise, one of them is going to be empty. So that's the rationale behind this condition. I don't remember what question you asked anymore.
You answered it. Thank you so much.
Okay. Okay. So this block structure basically means that these unit interval parking functions are these very nice objects that are very rigidly defined. And they also generalize permutations because permutations are exactly the 0 interval parking functions. So this is kind of like just one step above permutations. Speaking of permutations, we have to talk about Cayley permutations. So a Cayley permutation of length n is a word alpha 1 through alpha n. This notation of like bracket n to the nth power means the bracket n is the set 1, 2, 3 up to n. And raising to the nth power means we want tuples of numbers all between 1 and n. So a Cayley permutation is a tuple of numbers, all of them are between 1 and n, so that if 5 is in there somewhere, so is 4, and 3 and 2 and 1. Another way to think about these is they're sort of surjective words or permutations on 1 through k where you can have repeated elements, but you have to have one of everything. And they go by a lot of different names, and they're also in bijection with ordered set partitions. So to look at examples, 3, 1, 4, 1, 5 is not a Cayley permutation because it has 3 in there, but it's missing 2. You can't have these gaps in what the content is. But 5, 2, 4, 1, 3, 1, 4, 5 is a Cayley permutation because it has 1, 2, 3, 4, and 5 in its list. So there's no gaps in what it's got. And also, like, you have to have 1 in there. Okay. So I'm only going to explain this by example, but there's a bijection between unit interval parking functions and Cayley permutations, which preserves the set of inversions. So by set of inversions, I mean the set of pairs of positions where the earlier position has a bigger number than the later position. So an inversion is I and j, where ai is greater than aj, even though I is less than j. And this bijection gives us this, takes a word which is a unit interval parking function, spits out a word which is a Cayley permutation, and the set of inversions is the same. So to do this in an example, what we'll do is we take our unit interval parking function, and then we rewrite it in increasing order so we can see what the block structure is. This had 1, 1, 2, and then the next block is 4, the next block is 5, next block 6, 6, 7, and then 9, 9. Where this increasing unit interval parking function will go is we take everything in the first block, make it 1. Everything in the second block should be 2. Everything in the third block should be 3. Fourth block 4. Fifth block 5. And then to see what we want to do with our original unit interval parking function, you had to shuffle it one way to get the increasing version, and you just kind of unshuffle it after having replaced these numbers. So equivalently, you're writing down for each entry which block it appeared in the increasing thing. So this 9 was in the 5th block, so we write down a 5. Then the 4 was in the 2nd block, so we write down a 2. And we keep going like that. Okay, if you don't the important thing is that there is this bijection, so if you don't get every detail of it, it's okay. But any questions on this bijection or what a Cayley permutation is? Okay, I'm going to move on for now, but I can go back. Okay, so two true things are that the total number of inversions across all permutations, so that's, again, pairs of things which are out of order, is n factorial times n minus 1 over 4. And the total number of descents is n factorial times n minus 1 over 2. This problem of counting total inversions dates back to 1838, so it's a really old problem. And the descents, I don't know the exact date, but like this is a known thing. Schumacher proved that if you sum over all parking functions and you sum, oh, sorry, I have to say what descents are. A descent is an inversion where it's adjacent things. So you look at your list and you say, when is like A3 greater than A4? Or when is A4 greater than A5? So those are what descents are. So Schumacher proved that for parking functions, the total number of descents is n choose 2 times n plus 1 to the n minus 2. So we set out in this project to try to compute the total number of descents or total number of inversions for unit interval parking functions. That was one of the original goals. So what we do is something more general than this. And like I don't know how to describe how, like, I look at this now and I'm like, oh, of course you should think about expected value when you see these problems. But we really spent a long time thinking about these problems, not thinking about expected value at all. So you should come away from this talk thinking, if I see a problem like this, I should think about expected value if you didn't know to already. That's the moral of the story. When we finally got a proof involving expected value, it turned out to be a lot more general than just this problem. So if we take a word, so a sequence of numbers, we've got n numbers in our sequence, we'll define this chi ij inv function to be 1 if wi is greater than wj and 0 otherwise. So this is an indicator function for whether ij is an inversion. What we can prove is that if you take any Sn invariant set of words of positive integers, so we have a set of n tuples of numbers, so that if you permute the order of your numbers, it's still in your set, then the expected number of inversions is n choose 2 times the probability of an inversion in the first spot. The expected number of descents is n minus 1 times the probability of an inversion in the first spot. And as a consequence, the expected number of inversions is n over 2 times the expected number of descents. So I found this kind of surprising. I don't have more words for why I found it surprising, but I found it surprising that you don't really need to know very much to compute the expected number of inversions or expected number of descents, and that they're always linked to each other in this way. So does anyone want to guess about how to do this proof? It can be like a tiny guess, like just a starting idea. I'm gonna wait more time because the proof is not that hard and it's kind of very
So
nice.
you,
So
so
it's
you want to
fun to
relate
find it.
everything to the 1-2 inversion, right?
Yeah. So you can start with either like bullet one or bullet two and think about how do we get that. Don't start with bullet three.
So like for the first one, it looks like you're saying that overall n choose two pairs, there's the same probability that it's an inversion.
Yeah.
And then for the second one, you seem to be saying that overall, like n minus one, like positions, there's equal probability of it being a descent.
Yeah. Exactly.
So so you're taking the 1-2 window and you're sliding it, that gives you n-1. And for inversion, you're sort of like
Mhm.
spreading it over the whole permutation.
Yeah.
And then for the third one, it looks like you're just combining the first two.
Yeah. So if we just start with the left-hand side of one of these, we're just like, what's the expected number of descents? Then what should our first step, this is the right idea, but what should the first step be when we see expected number of descents? What can we do?
Sum over probability of each position being a descent.
Yep. And then we have to relate these positions. So this is like, 90% of the proof. Um, so here's how it goes with more symbols. Our we can write descents as summing over all of these indicator variables for whether there's a descent in each position. Then by linearity of expectation, we just need to compute those probabilities of a descent in any given position. Then we can take a permutation in the symmetric group that's going to send I to 1 and I plus 2 to 2. And we can use that to shuffle our word W. And when we do that, we'll get something, this sigma.w is going to have, like the event of an inversion in that first position is equivalent to an inversion in the I plus 1 position of our original thing. So the probability that originally we had an inversion in the I plus 1 position is the same as the probability that after permuting, we have an inversion in the first position. And because our set is permutation invariant, that's the same as the probability that originally we had an inversion in the first position. So this is showing that no matter which pair of positions you look at, the probability of an inversion is the same as if you just look at that first pair of positions. So when you apply this to the sum we had in the first set of equations, we have the expected value of the number of descents is this sum of expected values of whether you have an inversion, or sorry, whether you have a descent in the I plus 1 positions. And then those end up all being the same. So you have n minus 1 times probability of a descent in the first position. And the other proofs kind of follow similarly, where any ij, you can move it to the front and proceed like that. Okay, so what do we get from this? Well, unit interval parking functions are not permutation invariant, but Cayley permutations are, and they have the same properties around descents and inversions. So we get that the total number of descents, because we can pass between expected values and totals, the total number of descents in a over all Cayley permutations, or total descents over all unit interval parking functions. Sorry, we haven't proven this yet, but applying this, we'll be able to show this is n minus 1 over 2 times, sorry, I missed defining foob n. Foob n is Fubini numbers, which is the number of unit interval parking functions, or equivalently number of Cayley permutations. And it's a sequence that has lots of applications. But you get this n minus 1 over 2 times foob n minus 1. And something similar for inversions. And these are related by that, by this theorem. So briefly, because I'm running out of time, the way that you approach this is you say that in a Cayley permutation, the chance that my first two things do an increase is the same as the chance that they do a decrease, but they might do a tie. So if we can compute the probability that there's a tie in the first position, then we can figure out the probability that there's a descent or not a descent and not a tie. And we can do this with a bijection that if the first two things are the same, you just delete the first one, and it's a Cayley permutation of length n minus 1. This gives a bijection. We find that the probability of a tie in the first position is this foob n minus 1 over foob n. And then we can get the probability of an inversion in the first position, and we can get expected number of inversions overall. And that's how we prove this theorem. So also a consequence of this is we can do the same kind of argument that we just did for inversions and descents for ties. We can take any two positions in our word and move them around, and them being the same originally, they'll be the same after you move them around, and you can move them to the front, and you end up finding that the total number of ties is n minus 1 times foob n. A fun thing that you can also get from this is the probability of a tie in the first position is 1 over log 2 of E, and I just kind of like that, but that just comes from applying some asymptotic formulas on OEIS. So ties were not incorporated into the framework that we talked about, so how do we capture them? Well, I'm kind of out of time, so I'm not really going to go through it, but what we did in our paper is we defined this notion of a k-transitive function, which is just a statistic that is kind of compatible with permuting around your word. And inversions is a great example of this. And there's a lot of other examples of this. And given one of these sort of statistics that is compatible with moving things around, we define two versions of it. One which is analogous to descents, and that we're looking at kind of like adjacent positions, and the other is looking at, it's more like inversions, and we're looking at non-adjacent positions, and we can get all kinds of statistics in this fashion. And they all have these relations where you can just look at the beginning to figure out the overall expected value. And it also works, you don't really need SN invariant, you just need a k-transitive action. And anyways, these were some of the results that we got, and there were some other ones. And they're all very like fun that use this expected value point of view. Yeah, I'm happy to talk more about it, but that's kind of my time, so I'll end there. Oh, I have some bibliography, but it maybe got cut off.
Any questions for Gabe as we thank him for our emojis? Mm. So are there other statistics? I know you had that huge table that you keep flashing. Are there
Yeah,
any other statistics? It seems like as long as you have the property that like your set is SN invariant, plus your
the
like local enough.
yeah, the statistic sort of thing here is basically like it's something which is summed over different kinds of positions. And when you're looking at a position, you only care about the values of your word at those positions, not what the positions are.
Okay.
For any like pattern avoidance style condition, like saying like I have this sequence of things that are in this pattern of like these have these relative orders, then you can count both like adjacent instances of that pattern in your word and non-adjacent instances of that pattern in your word, and those sort of fit into this k-transitive framework. I kind of like these SDS is small descents, so it's like descents where it goes down by 1. Sinv is inversions where it goes down by 1. Peak is one of those pattern avoidance things where it's like, you have a thing and you go up and then you go down. So those are some of the ones that you can get. But I think you can get a lot of things in it, and I don't know. I guess I think it's a nice definition because it sort of gives this framework of thinking about what kinds of statistics are going to be really, really easy to compute the expected value of. Yeah, I don't know.
No, it's very cool, and I feel like it seems like the right way, as you've been highlighting, it's like the right way of thinking about things.
On that note, you can do all of this without expected value anywhere. You don't need probability, but the bijective versions of these proofs are not fun to write down because you have to keep track of like how you're splitting up a set and what you're doing with all the pieces.
That makes sense. Any other questions?
Yeah, I was curious about at least the bijective proof fact, because all of the parking function stuff has this n+1 to the n-2 happening.
Mm-hmm.
And uh, is there a more direct interpretation of that? So like parking functions have this nice, you have the parking function, you make it into a circle, and then you do like this nice proof.
Mm-hmm.
Is there a similar proof that you can do for these statistics?
I don't think this is answering exactly what you asked, but in some of these cases, we need to use that circle proof. So
Mm-hmm.
for ties and parking functions and for small inversions in parking functions, which are like kind of two very similar things, it's saying like two adjacent things are equal or two adjacent things are off by one. In both of those cases, like what our theorem tells us is, oh, you only need to compute the probability that this happens in the first position. But how do we compute the probability it happens in the first position? For those statistics, we use the circle proof. Um,
Mm-hmm.
and I guess, what what is it saying? So tie one is n+1 to the n-2. So we like divided by n-2 basically. So you do this proof that the probability of a tie in the first position is 1 over n+1, and that goes through the circle proof.
Mm-hmm. Mm-hmm. Makes sense. Hmm.
But
And
the
like
reason
a
you have
similar
the
idea. Yeah.
n+1 to the like n-1 everywhere is that you're looking at some probability times n choose 2 times the total number of parking functions. So the total number of parking functions is part of the formula.
Right. That would, okay. I see.
I'll briefly add that I forgot to put this on a slide, but there's a couple different open questions which kind of pop out of this because you can prove a lot of formulas this way. And then sometimes you get two formulas which look the same as each other. And then there's this question of how do I prove this bijectively? And part of me feels like you shouldn't. You should not prove it bijectively. At its heart, it's a probabilistic thing. But it's an interesting open problem to try to do bijective proofs of things coming out of these probabilistic proofs.
All right, since we're out of time, let me stop the recording and we can thank Gabe again.